Welcome everyone to the first new video of my new companion web series, and this is the first episode of We're Learning WebGPU, and we're going to use WebGL to actually learn this. So we're going to look at some code, and we're going to and just learn the API. This might be a long video, hopefully not. I always wing these videos, so if you're new to watching my stuff, I just wing it. I don't know what I'm doing. so first experience. So let's do this. I have like an intro video before this one that kind of shows you have to set up the browser and everything else. So I'm just realize you can't use your regular Chrome. You have to use Chrome Canary, and you have to set it up. So just look it up, or just look at the previous video, which I kind of show you how to do it. So WebGPU is a brand new API that's going to be the future of the web, 3D for the web. So we're going to learn how to do it, and I'm going to use WebGL as an example to get there. So if you're an experienced user of WebGL, great, because I'm going to use that knowledge to help transfer it over to this new API. So we can quickly look at some stuff, and here's what we're going to be making. We're going to make a simple triangle. All right. I really wanted to make point sprites like the first WebGL example that I made for my series, but WebGPU has no support for it, and it will never have it. So the bare bones, or the most basic thing you can actually do is lines, but I didn't even bother just to do a triangle. So I want to do something more fun like pixel sprites, but we're going to do a triangle example. And you can see just a triangle, and it spins. And I don't know if you can tell, but there's anti-aliasing, right? We're used to the anti-aliasing, unless we have to if we create our own frame buffers, we have to set up a certain way so we can get anti-aliasing. If you set up like a custom frame buffer and you don't do it in any it's a kind of like this like special type of sampling you have to turn on for custom frame buffers, else the edges get all jaggedy. So WebGPU, here's the WebGPU version of it. Always jaggedy. There is no anti-aliasing whatsoever. So that's one thing you should realize, is that you're going to have to work for nicer graphics on the WebGPU side, plain and simple. But overall, that's what we got. This is how we're going to do. We're going to do mirror images of WebGL and WebGPU and kind of see what the differences are. So here we go. So I can probably just get rid of it because we don't need that. All right. So we're going to look at some code. So we're going to look at the actual code. So I've broken down WebGPU into like 5 zones or 5 areas of introduction. So the first step is initialization. Like, how do we get it started up? How do we connect to it? How we get to begin the process of using the actual API. The next thing we would need to do is how do you do shaders. Shaders are the backbones of graphics programming. Everything has to be run through a shader. That's how things get actually rendered on the screen. The next things we need to deal with, so we got shaders, we got initialization, UBOs. WebGL, you don't need to use WebGOs, but because of WebGPU is incomplete, we don't have access to all the shader functionality. So the only way to pass data to a shader right now with the WebGPU is to use uniform buffers. So we'll walk through how to build uniform buffers for now. And the next thing, what is it? After we got shaders, how do we set up a mesh? That's another step. How do we how do we pass data? How to do buffers and things like that? That's another important step of it. And the final step is render. So we got init, UBOs, shader, meshes, render, and those are the 5 major steps of actually how to get things implemented and going. So I call this function init, but this is really just the start of the application. We're going to start the application. This is our application. This is basically our main function that we're going to run through. If we're doing a desktop application, main, and they'll start and it ends, and that's it. There's a render loop, but overall the render loop, all it does is just make the triangle spin. So the top part of the screen, actually I probably should make the GPU the top, and then make the WebGL the bottom. Probably makes more sense because it's the WebGPU series, right? So the top right now is the WebGPU version, and the bottom is the WebGL version. And as you can see, they're identical because that's what we want. We want to make an abstract layer that basically allows us to write the exact same function once, but uses 2 different APIs. So this is kind of like the beginning concept of an abstract layer. So like I said, we need to initiate the API. That's the first step. We need to set up a UBO so we can pass data into a shader. We want to set up a shader so we can do some rendering. We want to set up a mesh, so something we can render, and then we finally just render it. And like I said, the exact same code, same steps. The exact identical, and that's like the important part. So it's identical, but that's just because of our doing. So we're going to skip the rendering because that's the last step. So we're going to go into the API. The API is going to just hold like the important initialization. So here right here is the WebGL version. WebGL is actually pretty simple. We get the canvas, we get the contacts, we set up some default configurations, and we're done. That's all we really need to initialize WebGL. WebGPU is a little more complicated. It's similar, about the same, but it's a couple extra lines of code, and there's for good reasons why we need a couple extra lines of code. So I might have to stretch it out because there's quite a bit, a lot of comments. So if you're new to the series, be surprised. I write loads of comments, especially nowadays. All right. So the first thing we need to realize is that we have to kind of like download something called GLS-lang or GLS-lang. What this is a compiler. It's a C or C++ compiler that was written in C++ and then compiled into WebAssembly. So this way we can actually compile our shaders. Now WebGPU WebGPU has yet to pick a shader language. So there is actually no official shader language yet for WebGPU. What it does have has a bytecode type shader. It's based off of Spirv, SPIRV, and Vulkan uses that. So the whole it's an actually really cool idea about it is that the idea is you write a shader, and it basically can basically be any shader language as long as it compiles into this bytecode. Kind of like how it doesn't really matter which programming language you use, because eventually it all gets compiled into machine language, and that's what the machine understands. So this is how WebGPU and I believe Vulkan works. That you have to compile it, and then that compiled version is what you actually give to the GPU. You don't actually give the GPU your shader code at all. So this gives you a nice, cool, interesting feature is that for your production code, you never actually have to release any of your shader code. All your you can actually precompile everything and save that into your production version of your website or your web application or whatever, and that's what you load in. So that's actually a pretty cool, neat feature. So this way, ideally, you can then use any shader language you really want, as long as you can compile it down to this specific bytecode. So that's what we're doing here. So the first thing is we need to download the compiler, and I'm just using it. Instead, I don't have it locally set up. I just pulling it down. It just downloads a WebAssembly file, and it's actually about like a megabyte big. So the compiler is not a small piece for your website. It's actually a big piece. But like I said, in your final code, you don't need a compiler. Just compile it and save the actual bytecode, which is just like a float32 array or a uint8 array. I'm not sure. I forget which type it is, but it's just a big old byte array. So that's like number one. We need a way to compile our shaders. So that's the first thing we're going to do. We're going to download our shader compiler. Here's the first line of code that we need to do. We need to request an adapter. And what is an adapter? An adapter is basically the graphics driver. It's called an adapter because it's looking for something that's compatible with WebGPU, or it understands WebGPU or whatever. It can be used by WebGPU. So this means it can be a graphics card. It can be like a piece of software that actually does the rendering on the CPU. Whatever it is, it's some kind of adapter, some kind of driver on your machine that the browser can connect to and use it that can process its WebGPU code. So that's the first thing we need to do. We need to say, hey, browser, do you have any driver or adapter we can use so we can actually run WebGPU on? Once we have it, we get the access to the adapter. So we have a link to it. The next step after that is we take the adapter and we say request device. I don't know why they call it device, To me, it makes no sense, especially what it is. It's not really not getting a device. You're getting an instance. It's kind of like saying new GPU. So that's what request device kind of does. It creates an instance of the adapter. So this way now you can actually start using it. All our functions actually exist in device. In WebGL, all our functions exist in the canvas context. The canvas context actually is not really used much at all in WebGPU. It's only used for one thing, and we'll see in a little bit. So now that we have our, let's say, our graphics driver, and we made an instance of it, so we have the device, we're good and go. Now, the next thing we need to do is just create an instance of our compiler, because now we have a WebAssembly thing downloaded. Now we just need to run it and get it started and running, so this way we can use it, the compiler shaders. So the next step is now we need to do some canvas stuff. So we're going to get our canvas, and we're going to get a new context, and this context is GPU present. And in the WebGL, it's just WebGL 2. That's it. So it's same old idea. So once we have the context, and this is the only thing we need the context for, is that we need to use it to configure our swap chain. Now, this might be a new word for you, swap chain. But the swap chain does exist in WebGL, is that it's abstracted away from you. The idea of a swap chain is you have two frame buffers. You draw into one and you render the other. So let's say you have frame buffer A, you draw it and you say render. So now that's what's on the screen. Then you start drawing into frame buffer B. And when you're done, you do a swap. So now you're rendering from B and you have A free to draw. So you draw on A, then you swap, and you draw on B, then you swap. And that's what a swap chain is. That's all it is. It's just two frame buffers that get swapped back and forth. So our context from the canvas is where we get that frame buffer, that swap chain. So that's what a swap chain is. It's just really just a frame buffer. But like I said, WebGL has that in the background. It's just it was abstracted away. It kind of just did it automatically. I believe in OpenGL, you did have access to the swap chain, and you were able to control it, just like how we're going to be able to control it now. But in WebGL itself, they actually took that away from the user, because why bother? They can just take control of it and just let it run. So in this example, we don't need the depth buffer, but WebGL does have a depth buffer by default, so I just want to have it set up and go. So this way we have it. So you have an idea, it's like, okay, swap chain. That's what I probably should explain. Swap chain also, you have to configure it. So the starting configuration is that we give it the device, basically the instance of our driver, and then we give it a format. And that means the format is just how is the data stored in our frame buffer, because you can configure the frame buffer to store the data any way you want to. In this instance, the settings, where's the settings? Did I save it at the end? Let me hide this, hide that. So we have this configuration string we pass in, and what this string means is that we want to save RGBA, and we want this to be an unsigned normalized value. So most likely it's going to be like kind of like a float value, but it's normalized, so it's going to be a value between 0 and 1, but it's going to be a 32-bit. We also have configurations for the depth buffer. I actually didn't look up these settings, but if you're curious about the main frame buffer settings, we can kind of just pop this in really quick, and you can see there's a lot of configurations. There's quite a bit of them. And right here, the texture format kind of explains to you what it all means if you want to configure it for different ways. But the setting that I picked is what normally you're going to have. Another one that might be good, I don't know. Like if you need 64 bits, 128-bit, I don't know. But like I said, you can now customize how the data is laid out for whatever reason that you might need. So that's kind of like the important part for our frame buffer or our swap chain. So we need to configure it, and it's stored globally because we need to access it multiple times. So once you configure it, we need to do it multiple times. the next thing we need to do is then create our depth buffer. And our depth buffer in WebGPU is pretty much just a texture. So we give it a texture and we just give it some configuration. And we have to give it the width and height of that we want. I don't think it has to actually it probably has to match the swap chain, but it probably doesn't have to, because I've done frame buffers that are different sizes in WebGL compared to, like, so the main frame buffer is one size, but then the other one's actually smaller. I think when we were doing like shadows, so the shadow frame buffer can actually be smaller or a lot larger depending on how much data you want to store. So for this one, I actually made the depth buffer the exact same size as my canvas. So I'm not sure. I haven't really played around with it, but I feel like you probably can make it any size you want. But ideally, just try to make it the exact same size as your frame buffer. So everything should work just fine. It works for me. Like I said, I'm still kind of only been playing with it for like about a week or two. And that is our initialization. This is everything that we need to initialize WebGL. So overall, even though I have a lot of comments, it's not too bad. It's a little bit more verbose, but it's okay. It's no big deal. A lot of the stuff that makes it verbose is very boilerplate-ish. So it's one of those things you write once. You may make a special function out of it that can customize it a little bit here and there. But overall, it's going to be boilerplate. You put it away, and you'll probably never have to see it again. So that's the only thing you kind of have to get over the WebGPU part. It starts slow, but then once you get all the boilerplate stuff out of the way, then you can just run. Basically, you're writing your own API when you're using these things. You're writing your own abstract layer, so you can build it as easy or as difficult to use as you want. It's all up to you. So, like I said, it's not too bad. It's once you write it, you're done. Like ideally, you're probably not going to do too much with the depth buffer and swap chain. Like for most of the rendering I do, especially if you're doing a lot of prototyping, you're not doing a lot of crazy like rendering with light. This is good enough. You don't need anything else. You're done. Once you start doing like really fancy shaders, like physical based shaders, then you might actually need to add a couple extra like color buffers or whatever. Like if you want to do deferred rendering, we need to set up like 4 different color buffers. So the swap chain will have to actually have a couple more. I haven't looked up how to do that yet, but I've seen there's some examples of how to do deferred lighting already in WebGPU. So now we took care of initialization. Initialization is not too bad. Like I said, it's not too bad. So let's see what we got here. So we don't need that. And all the settings that we need for the WebGL is pretty simple. We just need canvas and the context. For WebGPU, we need a bit more things that we store. We need to store the canvas, which kind of don't use. In case we need to resize the canvas, we need it. The context, I don't think we need anything after that. We need adapter, we need driver, we need our compiler, we need our swap chain. This is something that's just going to be set and then unset when we do rendering. We'll deal with that. Same thing with pass. The way colors work in WebGPU, it's no longer an array. In WebGL, it's like an array of like normalized values between 0 and 1. We still have normalized values between 0 and 1, but instead of being an array, we have a structure. And WebGPU is very structure heavy. They call them descriptors and everything else, but you do a lot of a lot of structures, a lot of configuration. Then we have some of our settings. We have to create a depth buffer for rendering for every frame. We'll see in a bit. And then we have something called a render path descriptor. This is something that WebGL does not have. This kind of defines during our rendering process certain things. So it basically it's right now what this actually holds is our frame buffer configuration. Like what are our color buffers and where are our depth buffers, and attachment is the actual like texture that we have to apply. So every time we start a rendering process, or like every time we do a frame buffer, a frame draw, we need to basically set up our frame buffer for drawing, and we'll look at that when we do the rendering aspect of it. So, but that's the only thing is like we have this like configuration of how the entire frame buffer is laid out that's being done for rendering, for our shader rendering. And like I said, there's a lot of configuration. It's very verbose. Everything is very grained, like very fine grained, setup. So like I said, it's a lot of boilerplate. Once you have it really is. It's just a lot of boilerplates. I think the next thing we'll deal with is the UBO. Like I said, right now, WebGPU does not actually support uniforms for shaders. The only uniforms that we cannot use for shaders are related to textures, that we can pass in like textures to render. We can't pass in like types. We can't pass in floats. We can't pass in vectors. We can't pass in matrices. We can't pass in arrays. The only thing we can pass is a reference to a uniform buffer. So that is the only way with WebGPU that we can pass any custom data to it. Everything else, like we can do attributes and everything, but that's all more static data. But if we want anything that's dynamic, like dynamic data, like uniforms, that's what uniform data is for. It's more dynamic data that can change from object to object. We can't do it yet. It's not available for WebGPU. But if you look in some of the documentation, it says to do. So who knows? Once that feature's built in, I probably start to ramp up a little bit more work on WebGPU. So I'm going to be doing WebGPU stuff a little slow because I kind of need that. I don't want to build a system where you have to use UBOs like crazy for every little thing when I don't need to. So that's that's the only big given about using bleeding edge technology, is that it doesn't have everything you need yet to really build what you want. But right now it's good for learning to prototype and start building, just to get an idea, get our feet wet. So that's really what this whole thing is about. So if you don't know how to build what a UBO is just, like I said, it's just a uniform buffer, and all it is just the byte buffer array. And we store all the data in there. And WebGPU's uniform buffer is, by sounds of it, is almost identical to WebGL's buffer. Uniform buffer has the same idea. It's still 16-bit byte aligned. I'm not sure. I'm not sure it follows every exact same rule, but I'm assuming it does. Like a vector 3, then a float is not equal to a float and a vector 3. Like WebGL has a certain rule where every 16 bytes of the uniform buffer has to be accounted for in some fashion, and there's certain rules. Like if it's an array, even if it's a float, it's each float in the array is actually going to take up 16 bytes of information. Even though it's only 4 bytes, like it's just a float, it's going to take the entire 16-byte chunk. I think that's one of the rules for WebGL. Another rule was if a 16-byte chunk starts with a float, you can't put a vector 3 after it. You can do a vector 2 and then another float, or 3 more floats, but you cannot put a vector 3 after a float. And if you have a vector 3 starting a 16-byte chunk, you can't add a float to it. Oh, no, actually, sorry, you can add a float. So vector 3 and then a float is okay, which only equals out to be 16 bytes of information on the buffer end and on the GPU. But if it's a float, then a vector 3, then you're using up 32 bytes because you need a 16-byte chunk. And if you don't do the math right and you build your buffer wrong, data is going to go in the wrong way, and you're going to see disastrous results because it won't be the data you're passing in because they're incorrect. So all the data alignments need to be just right. So in my WebGL series, I built a UBO calculator that knows the rules. So this way, so you just pass in the data in the order that you want it, and it will actually then calculate all the offsets and the layout for the byte buffer, and then creates a nice a float array for you, so that you can just pass it to the GPU like nice and easy. So I might bring that back for this series. Just bringing the calculator. Probably don't bother explaining how it works because that's already been explained. But if there's new rules for WebGPU, I'll then explain those specific rules. Like I said, I need to look up and find the rules of how UBOs exactly work. The only thing I found out, it's still 16-byte aligned. And the same thing, like if you have is just one float in your UBO, which is 4 bytes, you need to fill in the remaining 12 bytes. So that's another important rule you have to remember, especially when you're using UBOs. If you don't, I know Macs will crash, because WebGL used to do that with me all the time. I never filled in my last remaining bytes of my 16-bit chunks, and the Macs would always crash. And once I fixed that bug, all my code started working on Macs just fine. So I had to help someone who had a Mac to help me debug that problem. So just keep that in mind. Every 16 bytes must be accounted. Your byte array needs to be in increments of 16 bytes. It has to be filled in. So if it's not divisible by 16, you're going to have errors. So that's the important part we have to deal with when we're dealing with UBOs. And this is the WebGL way of kind of setting up a UBO. So we have some data that we want to save. And again, I'm only going to pass in one float, but I need to fill in the remaining 12 bytes. So even though I only want one float, I need to have the remaining filled in. And then all we do is tell GL, create me a buffer, and then you have to bind it. Then you pass in the data, and you say it's dynamic because we're going to be updating it often. And then we unbind it, and then we set a bind bind position for it. WebGL has two different things. There's like a bind location and a bind point. So it's two different things, but WebGPU actually I think only has a bind point, and that's it. So it's actually slightly more simpler. So this is how we construct a UBO on the GL end. So if we're going to do this on the GPU end, so again, I didn't do that. It still works. It works just fine on Windows. Screw it, I'm just going to leave it alone. It works just fine on Windows, because Windows, everything runs on DirectX. And DirectX, I don't think has that requirement that every 16 bytes must be accounted for. It's something that's important for Macs. Macs Metal needs it. I'm not sure, and it's a rule for OpenGL as well, but OpenGL and the WebGL always worked over DirectX, so I never had this issue. So, like I said, I ran if you're on a Mac and it doesn't work, you may just need to fill in the remaining bytes for the buffer. So what else? So we create a buffer, and then we give it its size. And I think that the size is just bytes, just the byte size. So even though I'm putting one float in there, and I'm just setting as 4 bytes, it's everything. It works just fine. Just keep in mind, if you do add the extra zeros, the remaining the size actually going to be 16. It's 16 bytes long. So keep that in mind. I don't know if it works on Macs. I don't have a Mac to test. So if you want to check out this code on a Mac, and if it crashes, fix it so it kind of matches the WebGL a little bit more. I did a poor job making it mirror, and that's it. So the other thing we have to do is when we configure it, we have to say it's a uniform buffer. That's all we have to say. It's okay, this buffer that we're creating is a uniform buffer. So creating a buffer is a little bit more work, because we need that structure, like these descriptors. Where creating a buffer is a little bit more. It's very simple in WebGL. Just creating the buffer itself is very simple. And on GPU, it requires a little bit more. There's actually about a couple of other things. Next thing we need to do, we have to set up a bind layout. And this bind layout is for it's for the shader. So the shader knows exactly the bind position, the bind point that this UBO is going to be. Now, this doesn't actually have a reference to this specific UBO. It just says we're going to have a uniform buffer at that bind point. So I actually don't need to create this here, to be honest. This should be probably built somewhere else. But since it's related to UBO, I just do it in here. The one thing you kind of need to realize is a lot of these descriptors, we probably should create them once or make a collection of them and then reuse them. There's no point in like if I'm gonna create like 50 UBOs, which I won't. I shouldn't have 15 instances of this. I probably should have a function that says, give me, this whole thing, but just pass in the bind number. So this way it creates that structure, and then I get it. So this way, you don't duplicate all this code so much. So this way you can kind of make it a little bit easier. And on top of that, if let's say you're gonna have like these 12, or like you're gonna have these like maybe just 3 UBOs that's always going to be there, and they're always going to be bound to the exact same spots, you create this with just once, and then you pass it and you save it. So, and then you just reuse it for every UBO or for every shader that you create. So this is something that every shader that needs. So it basically, like I said, it only tells you that at this bind point there's going to be a uniform buffer, and that's it. Let's see. The next thing we need to set up is a bind group. Now the bind group takes the bind layout, but actually points directly to the UBO. So, like I said, we pass in the layout, or it's basically just saying, okay, there's going to be something on point 0, on binding 0, and then we're going to say on binding 0, this is the buffer, and it's actually the buffer that we created up here. So we kind of have the exact same thing here. So we have a binding for WebGL. So it's like the same thing as this, but different. So it's like I said, the WebGPU one is a little bit more complicated because we have to have those descriptors laying everything out. And that's everything. Like overall, it's not a lot. I have more comments than it is, but there's really not that much more to actually create a UBO. Creating a UBO for both is, I would kind of say, about the same. A little bit more extra code, but that's I can write all these into a single line, and it's no big deal, right? So yeah, it's really like one. If you're going to do like function calls, like that's one function call. That's 2 function calls. That's 3. That's it. We got 3 function calls. Over here, we have 1 function call, 2, 3, 4, 5. So technically, WebGL requires more function calls. It's more calling to the GPU to do things. So technically, WebGPU is better because it's less calls, but each call requires a bit more information. Now, the thing I really like about UBOs on the WebGPU version, this is how to update a UBO. And the way we update UBO, this is how we do in WebGL. You have to bind it, you got to pass the data into it, and then you got to unbind it. WebGPU, we just pass it to it. That's it. We're done. I love that. I love how simple and easy it is to pass information to a UBO in WebGPU. It's super simple. I really actually don't like all that binding. You have to use WebGL. But WebGL is a giant state machine, so you kind of have to do the binding because everything is single-threaded. This, since it's multi-threaded designed for WebGPU, it can get away with this in a lot of ways. So I really, really actually like about this the new thing. The new API. And I like that it's when we create that buffer object up here, like create buffer, that buffer actually has that method attached to it. Where when we create a buffer in WebGL, we're not actually creating an object. We're actually just creating basically essentially like an ID to the buffer on the GPU. So we always have to bind it and then pass in that ID number of that buffer. It's not really an ID with the way JavaScript builds it. It's still an object, but it's the same idea. It's just a reference back to the reference back right to it. Where WebGPU is an object that holds the reference, but then has methods to actually access the data and like manage the data. So it actually makes it a little bit easier in the long run. Once it's created, then you can just use it really easily. So that's like one of the big differences because we actually have an object. It's being designed a little bit differently. So that's UBO. So I don't know how long this video is already. 30 minutes. Oh, all right. All right. So next. And so now we know how to create a UBO, and we know how to create how to update the UBO. So the next step is we need to start dealing with shaders. Shaders for WebGPU is a bit more complicated. It works slightly different. So we'll quickly look at the WebGL version. WebGL overall might actually look more verbose, but the only reason why this version looks more verbose is because WebGL has a lot of functions that allows us to do error checking. Lots of error checking. So if there's like an error in the shader, I'll know before it's done being created, and so I can stop the application. I get an error message, and I'm good to go. I fix it, and then I can restart the page again. WebGPU, I haven't yet really found any like functions to actually give like to check. But the one thing I did notice in some of the documentation is that it seems to be very oh my god, the error like exception. It looks like it might be exception happy. So it'll just, instead of just you checking for errors, it'll just do an exception. So that may be how WebGPU I'm not sure yet, but like I said, I look at some documentation like on the website and I see things like throw this, throw that. I'm like, oh, so it's going to be throwing exceptions. So that's probably how the error handling might end up working in WebGPU. So we need to doing a lot of try catches in the future, as opposed to this one. We don't have try catches. We kind of have to check to see if the shader compiled or not. So in this way, we pass in our shader code. So first we create a shader, then we pass in our shader text, and then we compile it. Then we check to see if the compiling exceeded, it was successful. Then we do the exact same thing with our fragment shader. We create a new shader, we say it's a fragment shader, we give it the source code, we tell it compile. Then we check. If it's successful, we continue. Next step is that we need to link them together into a singular program, basically compiling them together. So we create a new program, we attach one shader, we attach the other shader, and then we compile it together, or link it. They call it linking. So now it's one program, one shader program, like one entire step. And then when we're done linking, we can do some error checking to make sure the linking was successful. And then we have an additional checks that we can do to make sure the linking was completely successful. And once the shader application has been linked, you can actually get rid of your shader object itself. So I read some documentation that says you can, but you shouldn't, because some hardware might not like it. I don't know, some mobile platforms might not like it. But overall, when it comes to Windows and on Macs, when you're done linking your shader, you can detach the shaders and you can actually delete them, and they're done. You get rid of them; they're not used anymore, because you have your link program, and that's all you need. And the last thing we need to do is we need to be able to bind our UBO to our shader. So to do that, we need to find out its bind location, or in this case, the block index of our UBO in our shader. So this way we can then tie our block index, the shader's block index can be tied to the bind point of the UBO, and that's how we link that to that. And then we're done. That's it. That's a shader in WebGL. Now the WebGPU version of a shader. So we're going to use the compiler that we downloaded. So we just compile it. So we compile our Vertex shader, and we compile our fragment shader. And that basically gives us bytecode of the SPIV, whatever it's called. It's the bytecode version of our shader. Then we say, well, okay, we need to create another descriptor, more descriptors, more structs. So we're going to have, this is going to be modules. So we want to create a module of our Vertex shader, and we want to take our Vertex shader. Basically, like I said, this is compiled. Even though it's compiled, it's not on the GPU. This is something we compile in memory in the browser, because this is a compiler we downloaded. So now we have that bytecode. We're actually going to send it to the GPU, and when we send it to the GPU, it's going to make it into a module. At that point, you don't, by the looks of it, you don't delete the modules. You need those modules to actually execute. So they're the ones that are going to be on the GPU executing. And you can actually mix and match. You can make. Well, I haven't got to that point yet. Let me keep going. So we just create a module, and we tell it what's the entry point. So all our shaders start with the main function. But I think at this point you can actually make a function called woot, and that could be your starting point. So if you want to have fun with it, you can change it from main to something else. I haven't tried it yet, but that's the whole point of the entry point main. So we set up our mod descriptors for each of our shader. And now the next thing we need to create a pipeline. Now, a pipeline can be considered the same thing as our linking program. So, like I said, that's why I want to show you the WebGL version. WebGL, we compiled the two shaders, and then we linked them together as a single application. You can look at the pipeline as a similar idea of linking our shaders together. Now, the idea of this is that, like the pipeline in the pipeline in Vulkan can actually have more steps. You have, like I said, you can have the fragment shader, you can have vertex shader, you have the geometry shader, and then you have telesense. I can't say the word telesense. Let's call it telesense or something like TESS, and then a bunch of more letters. It's a different type of shader that kind of like does a bunch of subdividing of your mesh. So you technically have 4 stages in your Vulkan. In Vulkan, you have 4 stages. WebGPU still only has 2 stages because compute shaders don't exist in this pipeline layout. Compute shaders in WebGPU has its own pipeline. So that one gets its own pipeline, and the one for rendering gets this pipeline. 2 separate pipelines. I think probably the other one will be called create compute pipeline. And this one just, that's it. So this is a layout, and the pipeline layout only kind of contains like certain configurations. And this is the bind layout for basically to say in this shader, there's bind 0, the bind point 0 is going to have a UBO, is going to have a uniform buffer. And that's all we do. So we have this layout, and then when we actually create the pipeline, we say, okay, here's our layout. Simple. And then we give it our vertex stage, our fragment stage, and then we have to configure it with primitive topology. Primitive topology is actually our old draw mode. In our old draw mode, we would say if it's a triangle, a point sprite, or a line, or a triangle strip or a line strip. We had multiple draw modes. In WebGPU, we only have I think 4 or 5 draw modes. I think it's 2 lines, 2 triangles, and the point. And the point in WebGPU is not a point sprite because we run everything in DirectX. In all honesty, and the point draw mode is only pixels. So you can actually set the point, but it would only draw a pixel. You can't actually change its pixel size, you can't change the point size, and you don't get point coordinates for the UVs. So no point sprites whatsoever, but we can draw pixels on Windows. I don't know what the hell happens if you run on Macs on Metal, but maybe just pixels again. So for so our shader has to be created with our draw mode predefined, where in WebGL I was able to create a shader. And then one frame I can render it as lines, and the next frame I can render as points, and the next frame, or I can have the exact same shader, and then render it. Render it for like multiple different types of data. So it was very versatile, be able to change the draw mode for every time every time I render with the shader. You can't do that here. In WebGPU, you cannot change the draw mode. The draw mode is static to the pipeline. So the entire pipeline is defined by the draw mode. So that means that we have to become a little bit more creative in how we create shaders in WebGPU. So I'll talk more about that when we're done looking at all the rest of the descriptor. So the next thing we do is the color states. Basically the same configuration we did for frame buffer. So that's why I have that value at the very top. It's the one that's RGBA 8 something, whatever. So that code is, we have to bring it back into our color state. So for every time we create a pipeline, we have to say, well, how is our frame buffer configured to save data? So we have to, again, micromanage the data configuration between our shader and our frame buffer. Then we have to set up our depth buffer. So we have to tell a shader, or at least the shader pipeline that we're creating right now, that we want to use the depth buffer. And since we want to use the depth buffer, here's all the configuration. So this is how we want the depth to be compared. This is how the data is going to be saved. Blah blah blah. Yakety schmackety. Again, very verbose. And then we have our vertex states, and our vertex states is our attributes. That's all it is. It's just configuring our attributes. And how did I set? In WebGL, we have to do the same thing, but we don't actually do it at the shader level. We actually can do it at the shader level, right here, bind attribute locations. But normally you don't have to, and most often you don't. You can if you really build a system very specific. But like for me, I never did. I actually I usually use VAOs in WebGL too. So all that stuff has been pre-configured in a different way. But in this version, we're not using VAOs because WebGPU does not use VAOs or anything like it whatsoever. So that's right. It's here. This is an example of how to bind the attribute to the shader, basically kind of like at compile time. But that's all. This is how we do it. That's the structure. We give it as an array. We have to give this the actual size. See, 2 floats. Oh, sorry, we're passing in vector 2s, so that means there's 2 floats, and that means there's 4 bytes for each float. So that means 4 bytes in total. So the entire stride length is 8. Even though we don't have, like, we're not doing interlaced data, we still have to specify the stride length. In WebGL, we didn't have to specify the stride length at all unless we was using interlaced data. In WebGPU, we always have to say, and it has to be by byte size. So, and then we just basically tell it the location that it exists inside the shader, which would be 0, has a 0 offset, and we have to give it the format. And in WebGPU, we're going to use float 1, float 2, float 3, float 4. I'm not remember sure how matrices are set up, but WebGL, we just used to say vec 1, 2, 3, and 4. So consider floats and vecs interchangeable. So that's actually a vector 2, x, y. And then we're done. That's it. That's the entire shader. So overall, it's not too much. We have 2 compiler calls, 2 shader calls, 1 pipeline call, or like pipeline layout call. It's just configuration, and and this is how we connect everything together, and that's it. So overall, it's like there's less. There's a lot less. It's actually, even though it's a lot longer, it's still a lot less code. Like, so it's just the descriptor. And like I said, all this is just mostly boilerplate. Now, like I said, now I'm going to go back to the whole point of the draw mode. Now, the biggest issue is now we have to be a little bit more creative when we create shaders. So let's say if I will create like a base shader that all it does is colors, like it does a basic color, no lighting, no whatsoever. If I want to, let's say, color a triangle and color a line, I need to create 2 separate pipelines. I need a pipeline that has a draw mode of a line, and I need a pipeline that has a draw mode of a triangle. So the idea, we have to be more creative than we did with WebGL. So the idea is that when we create these fragment, these shader modules, we might want to keep these shader modules around a little bit, because let's say, like I said, if we need to create 2 versions of this shader, we need to reuse them. So the shader functions are the same. The only difference is the draw mode. So we need to, so that's the one thing we need to keep in mind, is that when we create shaders in the future, we need to be able to reuse our shader modules to create multiple pipelines, just in case we need the exact same shader for different draw modes. So every draw mode basically ends up creating a separate pipeline, which essentially is just an entire shader. If you want to just look at it that way, you can look. Or you can, in my mind, on all honesty, no matter how you want to slice or explain to it, a pipeline is just a shader. We're just saying, here's my data, draw it, and that's what it is. That's it. The only difference is in this WebGPU, it's a little bit more complicated. I think I read they did it because it makes it faster. If you pre-configure everything, they can get more performance boost out of it, from what I've read. So that's why a lot of things are pre-configured with these descriptors. Again, all boilerplate stuff. Like it's very verbose, but it's boilerplate. This stuff can be configured. Like depth buffer. Like we can actually. The idea is that we can probably set up a few unique pieces. Like this part can probably be like maybe 2 or 3 different versions of it. One that has just the position, one that has position, UVs and normals, and one that has all 3 plus like some skinning information like joints and weights. And that's all the vertex states we need. So we can, like I said, we boilerplate like 3 or 4 versions of it, and then have a function that we can say, well, I want to the shader has to be able to use this type of data, data A, B, or C. We can be very creative how we do it. So, we can, like I said, we can define different shader types, and then just write functions say, I need shader type A or shader type B, and it can have all these configurations pre-set up just for you. So again, it's boilerplate, but it gives us some. We can be a little bit more playful or a little bit more creative in how we build our framework. Oh, almost done an hour. All right, we're almost done. So that's a shader. So shaders are, like I said, a little bit more complicated in a certain way. Now, the next thing is meshes. Meshes are actually very simple on both sides. So the WebGL version, we have to know how many elements are in there, and every element is basically how many vertex. So if you have like a float array that has like 9 different floats in there, but the element length is 3, that means it's a vec3. So that means our element count is 3. So let's say like the element length is 2, but the element count is 3 because we have 3 vertex, and for every vertex there's 3 floats. In this case, because we're doing 2D rendering, our element length is 2, but our vertex count is still 3 because we still are just rendering 3 vertices. So it's still 3, but for every vertice there is 2 floats. So what we do is am I missing something? Oh, never mind. So what we can do is create a buffer. We bind the buffer. We pass in the data. We actually pass the data into the function. So it's just a vertex array, which is a float 32 array. So we just pass it in. We unbind it, and we return the mesh object with the data filled in. So it's just our buffer, our count, and our length, and we're done. That's it. That's really all the data we need for a mesh to render. That's it. All done. For the WebGPU, that's it. It's actually just as simple, really. So we have our vertex buffer, we have our element count. We don't actually have to keep track of our element length, to be honest. We need the element length at the very beginning, but we don't need to save it. Because we do need element length later when we do the render process, but for WebGPU, we don't need to. It's pretty good. It's pretty simple. So creating a buffer, again, like I said, it takes a few extra steps. So you give it the size and length. And the beautiful thing about float 32 arrays, like type arrays in JavaScript, you can do length and it gives you how many floats there are, but there's also byte length, so it actually tells you how many bytes there are in your entire float 32 array. So that's great. It makes it super easy, because before I was actually calculating length times 4. Now it's like, oh yeah, I looked at the documentation. It's like, oh yeah, I could just use byte length. There you go. So it's very simple to just set length of the buffer. So we know. So we'd say the length of the buffer in bytes. We say a vertex. Oh yeah, it's a vertex. It's a vertex buffer it's a vertex array. I keep forgetting what this means, because there's not really that much documentation on what some of these settings are. So, but this is kind of like a bitwise operator. So it's just merging options together. So yeah, I don't know what copy destination means. I also see copy source somewhere. But like I said, the information for WebGPU is still very sparse, because it's still bleeding edge. They're still writing the API. And again, just like a buffer, we just pass in data very easy, no binding, no whatsoever. So we say, start at 0, I think, and that's it. And then we just save how many counts there are. So I have element length divided by the amount of floats there are, and that gives me my element count. Because when I do the rendering, I have to say how many elements do I want to render. And that ends our shader, or our mesh. Now we're almost done. Now we're gonna quickly look at the shaders. So we'll look at the WebGL version. So this is our vertex shader. So when we have position, it's going to be a vec2. It's at location 0. Here's our uniform buffer. We're going to just pass in a single float for an angle. Here's a nice function that actually does rotation based on an angle. So this way, I don't have to create a matrix whatsoever. Because I've seen other examples, and they create a matrix, and you have to pass in a matrix and all this. You have to start including a math library and all this jazz. I was like, you know what? For this example, I don't want no math libraries. I want to make this super simple. So I'm just going to pass in an angle in radians, and just have a function inside my shader that understands how to rotate a 2D point based on an angle in radians. And this is it. That's it. Very simple function. So all I got to do is just rotate it based on my angle, pass it into my vec3 or my vec4, and call it a day. And one thing, and that's it. And keep track, this is version 3.0 ES. And this is GLSL. And our fragment shader is very simple. Now, if I were to go to the WebGPU version of it, where'd that divider? There it is. It'd be great if we could see both at the same time. Probably not. Well, all right. So, you know what? Screw it. Just get rid of it for now. Here's our shader. Now, one thing you might notice, here's version 4.50. So this is a GSL version 4.5. So it's a newer version of GSL that we get to use. Again, everything is compiled to bytecode, and we have to download the compiler. So whatever, it doesn't really necessarily matter. But we have to set that up. You have to tell what version of the compiler. You have to tell the compiler what version we're using. So this is the version of the GLSL that we're using. Overall, it's the same thing. We still have layout, location, and everything else. The only difference is now, originally in the version of GLSL that we're using, we weren't able to set out a layout location by default in our shader code. In newer versions, we can set up our binding code, everything in there. So we can have actually everything predefined. Like in the GSL, we have to go find our bind index so that we can connect to it to our bind point. Now we don't need to do that because we have our binding value. So we can just say it's 0, it's going to be 0, that's it. There's no more discussions. There's no more interpretations. Set, I really can't find that much information. I found some information, but only on a Vulkan site. So like I said, I had to do a lot of reading and research to do this tutorial, because there's really not that much WebGPU information out there. I have like tons of links throughout all the comments, so it's worth to check out if you really want to read up on every piece of the API. It will help to understand, because it's, like I said, it's a little more complicated. Sets, I think, if I remember reading correctly, how Vulkan does is like you can actually have multiple sets. So I guess you can have like multiple layouts defined, and you say I want layout 1, layout 2, layout 3. So you can have basically probably the exact same uniform, but different versions of it. If I interpret it correctly, but like I said, again, I haven't had a chance to experiment with it or see any examples of it yet. Our rotate function stays the same, and our main function stays the same. Nothing has changed, and our fragment shader is the same as well. The only difference is we have to set the location for our out color. Here is just known automatically to be location 0. Done. Now the last piece of the puzzle, oh boy, finally, we're at the last piece of the puzzle, is rendering. How do we render our final image? Oh boy. All right. So this is the WebGL. So for WebGL, we got to update our UBO for every frame. We're incrementing our angle and we're updating our UBO. So we're just updating it. Then we got to call our begin render, and our begin render, which should be down here under API. We don't have to do much. All we have to do is clear our frame buffer. That's all we need to do in WebGL. WebGPU is a little bit more complicated. WebGPU actually has a render begin and a render end. But WebGL, very simple. The rendering is actually, to basically do basic rendering is actually a lot simpler in WebGL. Just one function call. You don't have to do like a lot of prepares and a lot of like ending things. So we do a clear. So now we have to bind our shader function or shader program. Then without a VEO, so like I said, we're not using VEOs because WebGPU does not have one. So we need to set up our buffer attributes or our shader attributes. So we have to enable the location 0. We have to configure location 0. So we're going to say that location 0, it's going to have this many elements. It's a vec3, like vec2. Sorry, vec2. It's gonna have a type of a flow, and I forgot what the rest of the configuration is. So now that we configured that attribute pointer, then we unbind it because we don't need to bound anymore. We bind the buffer, we enable the attribute, and then we configure the attribute, and then we just draw. And that's why I said we need element length, because we needed to configure the attribute. So, and then we draw, and this point says we have our draw mode. At this point, we can choose. I can change this to draw points, and it'll just draw the points instead of triangles, which is really very useful. Like, it really is really useful for prototyping. Sometimes I just want to switch over to points and to see the information, then switch back to triangles and everything is shaded. Like I said, it's useful for prototyping. Now it's going to be a little bit more difficult with WebGPU. I have to be more creative at how shaders are made. So I just start at 0 and at how many I want to continue doing. And that's it. Done deal. And then when I'm done, I unbind my shader program and then start again. That's it. That is my entire render process. Now, WebGPU's render process is a little bit more involved. So let's open up the render function. It looks simple. When you're actually doing the actual shader part of rendering, it's actually quite simple. But there's a bit of preparedness and completion that needs to be done. So the first thing to do is we're going to need to start our rendering. Oh my God, wait another hour. So we need to create something called command encoder. Now, that's what Metal calls it. Metal calls it a command encoder. Vulkan calls it a command buffer. But they're essentially the same thing. What this happens is that when you're doing rendering, when you WebGL, we're actually doing a bunch of GPU calls, and they're being executed sequentially as we're running through the loop. WebGPU doesn't do that. When we're doing it, we're actually recording our functions. our function calls. We're not actually executing anything on a GPU. So as we're going through this step, like set pipeline, bind pipeline, set vertex buffer, draw, all this is not actually executing right now. All we're doing is recording those functions. That's all we're doing. So this is where we record it to. So we're recording all our functions into our command buffer. And that's how the new modern GPUs work, or modern APIs work. Mitral, Vulkan, and DirectX 12, they all have some form of command buffers. And the command buffers can actually be filled in multi-threaded. So you can actually have multiple threads kind of building your command buffer, and then you kind of execute it all in one go. So once we have our command buffer set up for this render loop, we need to configure our render pass descriptor for our color buffer. So we go to our swap chain and say, well, get the current texture, which basically swaps, and then say create a view for it. So this way gives us access to the color buffer of our frame buffer, the color part of our frame buffer. And then we do the same thing for our depth texture. But the only difference is that we created a texture, and now we're going to say, well, give me a new view for it. So I think create view kind of just clears it out and wipes it clean for us, which is great. And our descriptor has the starting color for a color buffer. So this way, when I say, create view, and it clears it out for us, it just uses that default color in there. Now the next thing is, when we want to start rendering, we have to tell our encoder that we're going to begin rendering. And this configurations that we did, we set up the buffer. We set up our frame buffer that we're going to use for this render loop. We pass in the descriptor into our begin render pass. And this render pass allows us to create all our shader commands, essentially. So this is our pass encoder. So we have a command, we have our command encoder, and we have our pass encoder that just or render pass encoder that lets us do our thing. So now that we have our command buffer, we have our render encoder, we say, well, I got my my pass encoder, sorry. Too many things. And it's starting to get really late. What time is it? Oh, it's 11 o'clock. All right. So we got our pass encoder, and we need to set our pipeline. And just like how we had to do in WebGL, where's the render? We kind of have to do the same thing. We have to say use program. Here we say set pipeline. So same idea. Like I said, a lot of it's the same. The concepts are all the same. That if you look at these two programs like side by side, the ideas and concepts are the same. It's just the function calls are completely different and how you use them. But they are the same. You create a buffer. All right. So we bind our buffer. We have to bind our group, so this way we know our UBO was set up, or like it's connected to it, and then we need to connect our buffer to the array attribute, the attribute on the shader. We do the same thing here. We enable the vertex attribute, and then we configure it. We don't need to configure it. We just need to just say at position 0. This is the buffer that's going to fill in the attribute. That's it. Very simple. And then we draw. We just have to pass in the element count, and that's it. And that's basically our entire shader draw. Like this 4 lines of code, pretty much is this plus the use bind. So it's actually less code in general. Now, if I were to use just VAOs and I set up a VAO, this is all I need to draw. I just bind the VAO and say draw it. Done deal. So VAOs, like I said, it's more efficient and easier to use. It's a little bit more configuration. So in all honesty, when you set up VAOs, it kind of becomes just as complicated as it is in WebGPU. It's just complicated in a different way. But then it makes rendering a lot easier. because this way you don't have to, like, all this configuration data is configured into our VAOs in WebGL. Since we don't have anything like that, and I don't know if WebGPU is going to have anything like that. You're just going to have to we have to come up with a way to render meshes this way. You have to be able to have some of this configuration data set up before. Like normally I didn't have to really save the buffers. All I have to do is just save the VAO. The VAO was applied to our buffers. And then at the very end, we just have to do the render end. And the render end, let's see, it's right here. So when we're done rendering, we just tell our pass encoder that we're done. Then we then go to the device, get the default queue, because like I said, it's multi-threaded. So there's a queue of how our commands are executed, and we tell our command encoder that we're done, and the command encoder kind of just passes in like all the commands that we recorded, and then executes it. So like I said, it adds it to the queue, and when the GPU is ready, it'll execute the queue, and all the commands will then render our scene, and we're done, and it will just do the whole thing. And I left this here because when I actually started working on this, this is how I did it. You have to do device, get queue, and then submit. Literally today, it crashed. It would not work. And when I looked it up, it's because now it's called default queue. There's no function get queue anymore. There's just a queue that exists in the device. Then you submit. So this is an example that the WebGPU API is in flux. It is bleeding edge. It is bound to change, and anything you write today can and most likely will not work tomorrow and crash. And some of you might be saying, well, then what is the point of this last hour that we spent listening to your bullshit, right? It's going to change, but it's not going to change greatly. So, if you want to get your feet wet and get the ideas in, you want to. And like I said, it's a lot of boilerplate. And then if something breaks, you just fix that one piece in the boilerplate, and your entire application will work. I really don't think there's going to be a big, large fundamental changes. It's just a lot of incremental improvements and completions of the code. And so like I said, this was like a small little bug. If this was like a boilerplate render, I would just have to just change one line of code, and everything would just work, and it works again. So that's the only thing to keep in mind, is that if you're going to use WebGPU for now, things will break as it works toward a final version that will be available without turning it on, without Canary. And that's it. That's everything we need to do for WebGPU, and we're done. And that's rendering. Oh wow, this is a long one, and I'm tired, and my voice hurts. So, hope you enjoyed it. I know this might be a little complicated. It's different. Like, we have the command buffers, we have all the descriptors. We don't even have access to uniforms for our shaders, which kind of sucks. I really can't. Once uniforms are available for shaders, like regular floats and vectors and things like that, I would then probably spend more time working and probably making more videos. For now, I'm going to do it nice and slow. Keep reading and really spend a lot of time thinking about how to create the abstract layer. I'll probably bring ECS framework back in. I'm gonna have a new version of it, like version 3, that I've been kind of slowly putting together of ECS framework. So do that, and hopefully maybe the next video I'll probably deal with more bringing 3D into it. Getting our 3D world put together, have a grid floor. So this way we maybe spin around and maybe have 2 cubes in there, so we can actually test the depth buffer and things like that. So, and then I'm gonna have to start bringing in our math library, but the math library I created and I put together. I put together for for my WebGL application is workable, is usable, because the examples I've seen for WebGPU, they're using GL matrix, which is the exact same JavaScript library that you use if you want to use WebGL. Granted, I took pieces from that library to build my own, So it's kind of great. That means that my math library will work on GPU practically unchanged, because my entire thing is built off around float 32 arrays, where GL matrix, I think originally, which a lot of structs, but I think now it's switched over to arrays. I don't think float 32 arrays. I still use type arrays, because even though it's slower, I prefer to use types. And like I said, I make small prototypes, so there's not really a big performance. And I tested performance on float 32 arrays. There is performance if you're doing like 10 million instances of it, but I tested out an object pool. So if I create an object pool for my vector 3s and vector 4s and my quaternions, then performance goes back to normal as if I was using just regular arrays. So again, like I said, I'm 10 million or like 5 million instances. Like, I'm trying to push as many as I can. That's kind of unrealistic for the things I do, but at least I know if it ever becomes an issue, I can fix it right away just by using object pools. So I'm assuming the exact same thing rules into WebGPU, because again, at that point, it's not really WebGPU. That's really just JavaScript, and maybe hopefully the JavaScript engine will improve where float 32 arrays will be just as fast as regular arrays in JavaScript. And just as fast as using like structs. I don't understand how the object structure in JavaScript is somehow faster. It's just more optimized. Like it's had years of development, where type arrays are kind of new. So there's a lot of little things like that. But that's, like I said, that's mostly just a JavaScript thing and not necessarily a WebGPU thing. So yeah. So I hope you enjoyed it. I hope you liked it. I hope you're kind of excited. Like I said, because this is the modern way of doing it. So once you know how to use WebGPU, then you're like one step away from really just using Vulkan and Metal and DirectX 12. That's kind of like one of the main reasons why I want to learn WebGPU, because I get the chance to learn how the modern stuff works without actually having to set everything up, because WebGL, especially WebGL 2.0, is a great tool to learn. You don't need a compiler, you don't need a transpiler, you don't need nothing. All you need is Notepad and a browser, and at the most is a web server, because certain security features requires you to use a web server. Like, you can't load a texture into the GPU unless you're using a web server. But a web server, there's like a Chrome extension that runs a personal web server on your desktop. So that's like a simple fix. Like I said, it's an extension. You can download it in an instant, and you're good to go with Notepad, and you're done. So WebGPU is a great way to learn without actually setting up Vulkan. And Vulkan is actually a little bit more complicated when you set up. As I was reading Vulkan in relation to WebGPU, there's a lot more to it that I don't even know if WebGPU is going to go that far as Vulkan does. Vulkan requires a lot of synchronization, because, like I said, WebGPU is built off of the modern stuff, and it's multi-threaded. So if you're doing a lot of things that are multi-threaded, you need to synchronize. So Vulkan requires a lot more steps to do it, because like one thing, to upload a texture to the GPU, you don't just upload the texture to the GPU. You actually have to do it with a command buffer. You have to create that encoder thing, and so that gets executed first. So you kind of have to do that. So the way you render certain ways to upload data to the GPU has to be done through a command buffer. So if things are multi-threaded, you have to make sure your textures are up there before you render. So you need to do some synchronization. So I don't know if there's some automatic synchronization being built into WebGPU, or something we kind of need to start managing and dealing on our own. Kind of like how if you're actually building things in Vulkan. Granted, I don't have a lot of experience with Vulkan at all. This is the information I've been reading for the past 2 or 3 weeks as we're preparing for this video. So yeah, so like I said, this is a great chance to learn, and it like gives you a head up to get started with modern APIs, especially if you want to go into Rust and start doing desktop. This web stuff makes it super easy to learn, and gives us a chance to really, really do it. And so I'm really excited. I'm losing excitement because I'm getting tired and my voice is dying. So let's see, it's almost already an hour and 20 minutes. So I guess I'll end the video. Again, thank you for watching. If you sat this long to listen to my bullshit about WebGPU code, I'm sorry this video was really long, but maybe there's a lot to get started with WebGPU, and it's like I said, it's more complicated. But hopefully, if you like it, tell me. I'll try to make an effort to try to make more videos about it. Like I say, I want to do it slow. But if people are really excited about WebGPU, I'll try to put more effort into learning it and building more lessons around it. Yeah. So if you enjoy this, please like and subscribe. Helps the channel out a little bit. Eventually I'll be able to monetize at some point. I still can't monetize almost after 3 years, so who cares? Whatever. If you want to support me, I have a Patreon. Just $1 tip goes a long way. So thank you for any help you want to give. If you don't, that's fine. I just like to teach and show people how to do it, because if there's enough people that know it, then there's enough people that can teach me a new trick here and there. So spreading the knowledge. Got to do it, right? As they say sometimes, those who can't do teach. I can't do it professionally, so I might as well teach people that probably have the opportunity to do it, right? So thank you for watching, and I guess I'll see you guys in the next video. If anything, I'll see you in the next WebGL video, which hopefully will be soon.